Imagine holding a winning lottery ticket.
Okay.
You glance down at the numbers, you give a little shrug, and you toss it right into the nearest trash can.
Which is painful just to even think about.
It really is. But that is exactly the scenario the executive team at Intel found themselves in back in 2005.
Right.
They were sitting on an opportunity to acquire this scrappy, honestly somewhat volatile graphics chip company for roughly $20 billion.
And Intel, I mean, at the absolute height of its power.
They passed.
Oh,
They
yeah.
just passed.
Yeah.
The prevailing wisdom in that boardroom was, well, we can simply engineer our own integrated graphics technology. We don't need them.
Right.
Fast forward to today, the year 2026. That scrappy little company is Nvidia.
Yep.
And they are now a $3 to $4 trillion behemoth, arguably the most valuable single corporate entity on the planet.
And Intel is the one aggressively navigating acquisition rumors just to survive.
Exactly. It's wild. Welcome to the Deep Dive, everyone. Today we are mapping the underlying architecture of the AI industrial revolution.
It really stands as the ultimate technological what-if of the 21st century.
It does.
Our mission today for you is to decode the precise engineering, the financial, and honestly, the cultural mechanics that facilitated NVIDIA's $3 trillion ascent.
And to do that, we are synthesizing a really massive stack of source material for you today.
A huge stack. We're analyzing a remarkably candid, deeply technical interview with NVIDIA's co-founder and CEO, Jensen Huang.
Right. We're also evaluating their fiscal year 2024 sustainability report.
Cross-referencing that with their Q3 FY 2026 financial breakdowns from Voronoi.
And then we're overlaying recent market and geopolitical analysis from the Ridgeway Record and The Guardian.
Because we are examining a 30-year trajectory here, we need to understand how a very specific set of architectural philosophies compounded over decades.
And the fascinating aspect of this trajectory is that, well, we aren't fundamentally just discussing microchips today.
No, not at all.
We are looking at an ongoing masterclass in this strategic concept known as $0 billion markets.
Which is such a great phrase.
It is. We are tracking how an organization that initially just dedicated itself to rendering better textures in PC video games.
Making water look like water.
Right, exactly. How they evolved into an entity that models the Earth's climate and powers the foundational layer of generative AI.
It is a complete redefinition of what a computer actually is.
It really is.
And the computer science behind this evolution is incredibly dense. So we will dissect it rigorously for you. We'll translate the engineering bottlenecks into relatable architectural concepts.
And most crucially, we'll explore the causal relationship between what Nvidia built and why their highly unconventional corporate topology made those builds possible.
Because their dominance isn't simply a byproduct of superior silicon manufacturing.
Right.
It is the result of a very specific, almost antagonistic approach to traditional corporate forecasting.
Yeah, Jensen Huang's concept of the $0 billion market is the perfect entry point for that antagonistic approach.
It is.
He describes this strategic imperative to navigate toward non-consumption.
Which sounds crazy.
Right. For anyone operating in a traditional corporate environment, this is incredibly counterintuitive.
Yeah.
Picture a pioneer looking to establish a new settlement.
Okay.
The standard business playbook dictates that you walk into a dense, bustling forest where a timber industry already exists.
Where the money is.
Exactly. And you fight fiercely to carve out your own little acre to build a cabin. You do this because the market is proven. You know there's demand.
The total addressable market is clearly defined, it's quantifiable, analysts can model it for you.
Precisely. But NVIDIA's methodology is they walk entirely away from that forest.
Just totally the other direction.
They hike miles out into a completely empty, barren dirt field.
Yeah.
And they pitch a tent.
And the broader industry looks at them as if they have completely lost their minds.
Exactly. But they pitch the tent because they have conducted this exhaustive analysis of the soil composition.
The subterranean water tables.
Yes, the microclimate. They know with mathematical certainty that a massive, lush forest is going to spontaneously grow around that exact coordinate 10 years in the future.
Right. They endure the barren field because they intend to own the forest.
Exactly.
And when you apply that analogy to corporate strategy, the brilliance is obvious, but But the execution is fundamentally terrifying.
Oh, absolutely terrifying.
Pitching that tent in the semiconductor industry requires deploying billions of dollars in capital expenditure.
Tens of thousands of engineering hours.
Over a decade, before a single end user actually requests the product.
And the modern publicly traded corporation is designed to optimize for quarterly earnings.
Right. Wall Street aggressively punishes any deviation from short-term profitability.
Brutally punishes it.
Therefore, navigating toward a $0 billion market requires a tolerance for financial pain that is incredibly rare. You are entirely funding a speculative future using the margins of your present.
And that tolerance for pain, it wasn't born out of abstract theory. It was forged in a very literal near-death experience.
Yeah, 1997.
Right. If you wind the clock back to 1997, Nvidia was facing total insolvency. They were developing the RIVA 128 chip,
Which was engineered to be the first fully 3D accelerated graphics pipeline for a consumer PC.
The engineering was ambitious, but the balance sheet was disastrous. They had exactly 6 months of operating runway left.
6 months, and the physical realities of semiconductor manufacturing in the late 90s made that 6-month runway a ticking time bomb.
Because it's so slow.
Right. The historical precedent for chip design is highly iterative. You design a circuit, you commit it to physical silicon, a process known as a tape-out.
Right.
You wait months to receive the physical prototype back. You test it to discover the inevitable microscopic flaws. You redesign, and you tape out again.
And each cycle is exorbitantly expensive and intensely time-consuming.
Yes.
Traditional chip manufacturing at that time was akin to, well, think of it like publishing a massive 1,000-page technical manual. But instead of running a spell checker on your word processor, you send your handwritten rough draft directly to an industrial printing press.
And you pay them to print, bind, and ship 10,000 hardcover copies to your warehouse.
Exactly. And only then do you sit down with a red pen, read through the physical books to find your typographical errors.
Throw all 10,000 copies into an incinerator.
Yes. And pay the printing press to start over.
Which is insane.
It is. But NVIDIA's executive team looked at their remaining capital and realized they only had enough money to run that printing press exactly once.
One time.
A single critical flaw in the physical silicon meant immediate bankruptcy. End of story.
So facing that absolute binary outcome, survive or die, they made a decision that altered the entire trajectory of the company.
They decided to prefetch the future.
Right. They utilized a significant portion of their remaining capital to procure an emulator.
Which, in the context of 1997,
was essentially a massive, highly inefficient supercomputer designed to mimic the exact logical behavior of their unbuilt RIVA 128 chip entirely in software.
they built the ultimate digital skull checker.
Exactly.
But, and we need to stress this, the term emulator makes it sound seamless, which it absolutely wasn't.
Not at all.
The source material details how agonizingly slow this process was. Running their graphics software stack on this emulator took an entire hour just to render a single frame.
One frame.
One frame of the Windows operating system boot screen.
Wow.
Yeah. Engineers sat in a dark room, watching a monitor paint pixels one by one, debugging drivers against a virtual ghost of a microchip.
Just a simulated purgatory.
Right. And they operated in that purgatory until they achieved absolute mathematical certainty that the design was flawless.
And only then did they commit their final dollars to a physical production run, entirely sight unseen.
And the climax of that gamble is where the engineering reality really collides with market timing.
Yeah. The chips are manufactured, they arrive at the lab, and they power them on.
Success.
But simultaneously, Microsoft had just released the DirectX API.
Right, which established 32 distinct graphical blend modes for rendering 3D environments.
And the RIVA 128 Silicon natively supported exactly 8 of those 32 modes.
8 out of 32.
Right. By traditional metric standards, launching a piece of hardware that only supports 25% of the new industry standard is a catastrophic failure.
A total flop.
Right.
But those specific 8 blend modes were executed with such mind-bending, unprecedented speed that the consumer market completely ignored the missing 24.
It just didn't matter.
Not at all. The raw performance completely blinded the industry to the architectural compromises.
And Jensen Huang extracted a foundational philosophy from that survival story.
Speed is performance.
Speed is performance, and time to market is performance. Why incur the financial and temporal cost of doing something twice if you can simulate it perfectly and execute it once?
By dragging all the latent risk forward into the simulation phase, they bypass that iterative physical trap.
Exactly. This wasn't merely a tactical victory in 1997. It became the central dogma of NVIDIA's engineering culture.
Prefetch the future.
Yes. Stress test reality in a synthetic environment, and when you finally commit to physical manufacturing, operate with total certainty.
So having survived the RIVA 128 crucible, they aggressively captured the video game graphics market. But dominating a hardware niche wasn't the end state.
No, they recognized an existential ceiling to being a pure component supplier. They needed to execute a transition from a product company to a platform company.
And that distinction between product and platform is paramount when we're evaluating tech valuations.
It really is. A product is a discrete solution to a specific problem. A consumer purchases a GPU to render higher frame rates in a video game. That is a transactional product relationship.
You buy the thing, it does the thing.
Right. A platform, however, is a foundational layer upon which external developers construct their own products and businesses.
Like Windows or iOS.
Exactly. Countless hardware companies have released press releases declaring their intent to build a platform, and almost all of them evaporate.
Because you can't just declare it.
Right. You cannot simply will a platform into existence. You must establish indispensable underlying technology and then meticulously construct the platform architecture beneath it, often against the desires of your own users.
And Nvidia certainly didn't get this right on the first try.
No.
The sources detail their early, highly aggressive attempt to establish a proprietary platform called DirectNV.
Which was aimed right at Microsoft.
Yeah, they wanted to directly challenge Microsoft's DirectX ecosystem. And it was a brutal miscalculation.
Because Microsoft owned the developer relationships.
Nvidia was soundly defeated. They realized you cannot declare war on the dominant ecosystem. You have to insinuate yourself as the bedrock beneath it.
And that failure birthed what is arguably the most consequential strategic pivot in the history of modern computing architecture.
CDA?
The introduction of CUA, or Compute Unified Device Architecture, around 2006.
So to understand the magnitude of CUDA, we really have to look closely at the architectural constraints of computing at the time.
Okay.
We all know a standard CPU is heavily optimized for sequential serial processing.
Right.
It is brilliant at executing complex single-thread logic incredibly fast. One thing after another, blazing speed.
But Jensen foresaw that the bleeding edge of computational science wasn't going to remain strictly serial. It was going to require massively parallel execution.
Doing thousands of things at once.
Exactly. A GPU is fundamentally a parallel architecture. Instead of a few incredibly fast cores handling complex logic sequentially, a GPU possesses thousands of simpler cores capable of executing concurrent parallel execution pathways.
It's designed to calculate the trajectory of 1 million polygons simultaneously for a video game.
Right. And NVIDIA realized that this parallel architecture could be weaponized for high-performance scientific computing, not just pixel rendering.
But there was a massive bottleneck.
A huge one. You couldn't just ask a fluid dynamics researcher to write their simulation code using graphical shading languages.
It was structurally impossible. It's like asking an accountant to do a tax return using only sheet music.
Exactly.
So CUDA was the Rosetta Stone.
Yeah.
It was a proprietary parallel computing platform and programming model that allowed software developers to use standard programming languages like C++ to map complex mathematical problems directly onto the GPU's concurrent cores.
But, and this is the critical part, NVIDIA didn't just release CUDA as an optional software add-on.
No, they didn't.
They instituted a militant, uncompromising mandate across the entire company. From that day forward, every single microchip NVIDIA fabricated would be fundamentally compatible with CUDA.
Every single one. And the capital expenditure required to enforce that mandate it's difficult to overstate.
Yeah.
Think of the computing hardware market as a fractured landscape where every municipality builds a rail network with entirely different track gauges.
Code written for a highly specialized supercomputer node was utterly useless on a consumer workstation.
Totally useless.
So NVIDIA imposed a universal railway gate.
Yeah.
They dictated that every piece of silicon they manufactured, from a $200 consumer graphics card to a $50,000 data center accelerator, would execute the exact same instruction set.
Which means a university researcher could prototype an algorithm on their inexpensive desktop PC on a Friday night
Right.
and deploy that exact same code flawlessly across a multi-million-dollar server cluster on Monday morning.
They forced architectural compatibility across hundreds of millions of distributed nodes over decades.
And the financial reality of building that universal railway was brutal.
It was. The sources indicate Nvidia absorbed roughly 10,000 person-years of engineering investment to develop and support CUD before the broader market even grasped its utility.
10,000 person years, and Wall Street analysts were merciless.
Oh, absolutely.
They demanded to know why a highly profitable video game component manufacturer was incinerating billions of dollars in R&D to provide free programming tools to a microscopic niche of academic researchers.
Right. Nvidia's stock price didn't just dip. It suffered devastating 80% collapses on multiple occasions.
80%. Imagine being an investor watching that.
Well, consider the immense psychological fortitude required to manage a publicly traded entity through an 80% devaluation.
That's unfathomable.
You are standing in front of institutional shareholders who are explicitly demanding that you terminate your expensive esoteric science project and maximize the margins on gaming hardware.
But they didn't.
No. Sustaining that vision required Jensen Huang to cultivate a board and an investor base with an ironclad belief system.
The source material highlights Don Valentine of Sequoia Capital, one of NVIDIA's earliest institutional backers.
Yeah?
Valentine was notoriously demanding. He famously told Jensen, "If you lose my money, I'll kill you."
Which is, yeah, quite the motivator.
Right. But he possessed the rare capacity to understand long-term architectural plays. During the most severe stock collapses, he would send Jensen encouraging notes over clipped newspaper articles highlighting the pessimism.
They absorbed the market punishment because they understood they were pouring the concrete foundation for a $0 billion market that was inevitably going to detonate.
And that detonation occurred precisely in 2012.
Yes.
We call it the Big Bang of modern AI.
The detonation took place within the confines of an academic computer vision competition called ImageNet.
Right.
For 3 decades prior, the discipline of machine vision had been trapped in a methodology of explicit rule writing.
Software engineers would attempt to construct exhaustive logical frameworks to identify objects.
Right, they would write code stating, if you detect an arrangement of pixels representing 2 pointed shapes above an inverted triangle, accompanied by horizontal linear patterns, classify the object as a cat.
But the physical world is infinitely chaotic.
Exactly.
If the cat is partially obscured by a shadow or viewed from an oblique angle, the explicit rules shatter.
The software fails entirely. The approach was inherently fragile.
Then a coalition of researchers submitted an architecture called AlexNet.
And they entirely abandoned the explicit rule writing paradigm.
Right. They utilized 2 consumer-grade NVIDIA GPUs, leveraged the CUD platform we just talked about, and processed an enormous data set of millions of labeled images.
Using a technique called deep convolutional neural networks.
And AlexNet didn't just win the ImageNet competition. It achieved an error rate so dramatically lower than the runner-up that it effectively rendered 30 years of human-coded software obsolete in a single afternoon.
A single afternoon. AlexNet proved the viability of a profound mathematical concept, the universal function approximator.
So to conceptualize the sheer scale of this shift, think about how we traditionally instruct computers.
Okay.
Traditional programming is like managing a highly rigid industrial bakery.
Right.
You provide the machinery with an unalterable recipe. Exactly 400 grams of flour, 200 grams of sugar, baked at exactly 350 degrees for 45 minutes.
And if a single variable is off, the process fails.
Right. But the universal function approximator is like providing the machinery with an infinite warehouse of raw ingredients, showing it 10,000 photographs of perfectly baked cakes, and instructing it to derive the methodology on its own.
It mathematically approximates the function of baking.
Exactly. The system iterates millions of times, failing repeatedly, dynamically adjusting its internal weights and biases until it organically synthesizes a recipe that succeeds universally.
And Jensen Huang observed the AlexNet breakthrough and experienced a profound strategic epiphany.
Right.
He realized that for the vast majority of highly complex human and industrial endeavors, causality is completely irrelevant.
And this is a massive philosophical pivot. Explain the distinction between causality and predictability in this context.
Well, in traditional scientific and commercial modeling, we expend immense resources attempting to isolate the why.
Right.
Why does a specific demographic of consumer purchase mustard when they purchase hot dogs? Why does a highly specific permutation of atmospheric pressure and humidity generate a particular cloud formation?
We want to know the underlying reason.
Exactly. But Jensen realized that we don't actually need to comprehend the underlying psychological or thermodynamic causality.
We just don't.
No. We merely need a computational system capable of perfectly predicting the outcome.
Wow.
We don't need to know the psychological trigger. We just need a mathematical guarantee that the consumer will buy the mustard so we can optimize the supply chain.
We don't need to unravel the chaotic thermodynamics. We just need a flawless prediction of precipitation so we can route logistics networks.
Causality is an academic luxury. Predictability is immense commercial power.
And once that realization solidifies that causality is out and predictability is in, it becomes obvious that deep learning isn't just a novel technique for categorizing internet images.
Not at all.
It is an entirely new methodology for manufacturing intelligence.
Yes.
It is a universal tool capable of revolutionizing logistics, pharmaceuticals, material science, and financial modeling.
Which brings our timeline to 2015.
2015.
Nvidia is completely re-architecting its strategic roadmap around this new paradigm.
Yeah.
A small, highly ambitious research organization named OpenAI is incorporated.
Right.
And Jensen Huang makes a highly symbolic and strategic move. He personally delivers the world's first AI supercomputer in a single chassis, designated the DGX-1, directly to Elon Musk and Ilya Sutskever.
And the physical specifications of that DGX-1 mentioned in the sources are fascinating.
Yeah.
It wasn't just a powerful server. It was a 70-pound monolithic block of computation containing over 35,000 individual components.
NVIDIA wasn't just observing the AI gold rush. They were hand-forging and hand-delivering the industrial-grade excavation equipment before the broader market even realized the territory held gold.
The DGX-1 really symbolizes the moment NVIDIA fundamentally redefined the physical manifestation of a computer.
It did, because for its entire history, NVIDIA was intrinsically tied to the desktop form factor.
Right, the PC beneath your desk.
Their core product resided inside a chassis, bound by the physical constraints of a single motherboard. But Jensen extrapolated the compute requirements of deep learning and concluded that the processing power required to train these massive neural networks could no longer be contained within a localized environment.
The computer had to become the data center.
Exactly, the entire data center.
And this transition from the desktop to the data center wasn't an instantaneous leap.
No, it took time.
The sources map out a highly methodical 15-year stepping stone strategy. They didn't just wake up and start building hyperscale infrastructure. They iterated toward it.
Right. They began with a concept called cloud gaming, a platform known as GeForce now.
And the engineering challenge there was wild. You have to render a graphically intense video game on a remote server rack and stream the high-fidelity video output to a highly underpowered laptop over standard consumer internet protocols.
With imperceptible latency.
Right. If there's lag, the game is unplayable.
Exactly. And from there, they expanded into remote graphics virtualization for high-end enterprise workstations.
So by the time generative AI truly necessitated planet-scale data centers, NVIDIA had been aggressively optimizing data center architecture for over a decade.
And we can quantify the absolute success of that architectural pivot by examining the Q3 FY 2026 financial data sourced from Voronoi.
The numbers are staggering.
They really are. In that single 90-day period, NVIDIA's data center revenue hit $51.2 billion.
$51.2 billion in 90 days.
Right. That single division now accounts for nearly 90% of the company's total aggregate revenue.
Conversely, their gaming division, the foundational market that capitalized the company's early existence, generated $4.3 billion.
Representing a mere 7.5% of the total.
Wow.
If you look at the preceding two-year window, data center sales exploded by 253%, while gaming growth stabilized at 49%.
They successfully executed a complete corporate metamorphosis.
They are no longer a component supplier for the entertainment industry. They are the foundational bedrock of global computational infrastructure.
But, and this is a massive but, engineering a data center optimized for training large language models is entirely different from engineering a data center optimized for serving e-commerce websites or streaming video.
It's a completely different beast.
Which brings us to a critical technical constraint, the battle against physics. Specifically, the battle against the speed of light.
Yeah. When an organization trains a massive trillion-parameter generative AI model, They are not executing code on a single, incredibly powerful processor.
The computational workload is vastly too large for that.
Exactly. The task must be distributed across tens of thousands or even hundreds of thousands of individual processors networked together across a massive physical facility.
And this is exactly where traditional hyperscale networking infrastructure fundamentally collapses.
Standard cloud computing environments utilize Ethernet networking protocols, specifically TCP/IP.
Right. And to make the limitations of TCP/IP tangible, let's consider the analogy of a massive high-density apartment complex. You have thousands of residents coexisting in the same physical structure. They utilize the same municipal water lines, the same electrical grid, the same elevator banks.
Sure.
But their daily lives are highly asynchronous and entirely independent.
Right.
The resident in apartment 4B streaming a movie at 2:00 a.m. has absolutely no interaction with the resident in apartment 7A who is baking a cake at 4:00 p.m.
Right. The underlying infrastructure simply needs to possess sufficient total bandwidth to accommodate everyone's independent demands simultaneously.
It just needs to be good enough most of the time.
And that is the perfect encapsulation of traditional hyperscale cloud computing.
Independent tasks.
Exactly. But training a frontier AI model is not an apartment building.
No.
It is a massive symphony orchestra comprising 100,000 musicians.
Wow.
Every single processor in the cluster is executing a highly specific mathematical operation that is intrinsically linked to the exact operation being executed by every other processor.
So if the string section receives their sheet music a fraction of a millisecond later than the percussion section,
The entire symphony instantly devolves into catastrophic noise.
the model fails to train.
Yes. The processors must exchange petabytes of parameter data flawlessly, synchronously, and continuously. In this environment, raw bandwidth is secondary. Ultra-low latency is the absolute paramount metric.
And the ultimate hard constraint on latency is the speed of light.
Exactly.
The physical data literally cannot propagate through optical cables fast enough to maintain perfect synchronization across a massive physical facility if you're relying on the processing overhead of standard Ethernet protocols.
It's just physically impossible.
So Jensen recognized that the communication bottleneck was going to choke the compute capabilities of his GPUs.
Yeah.
What was a strategic countermeasure? He acquired a company named Mellanox for nearly $7 billion.
And at the time of the acquisition, many market analysts were completely baffled.
Why would a GPU manufacturer acquire a highly specialized networking hardware firm?
Right. Mellanox was the preeminent leader in a proprietary networking standard called InfiniBand.
Which was almost exclusively utilized in highly specialized academic and governmental supercomputers.
But Jensen understood that in the era of distributed AI training, the individual GPU is no longer the computer.
The network itself is the computer.
Yes. InfiniBand utilizes a technology called Remote Direct Memory Access, or RDMA.
And what did that do?
It allows one processor to read and write data directly into the memory of a totally separate processor across the facility, completely bypassing the operating system and the CPU overhead of the receiving node.
So buying Mellanox was not just an acquisition.
No, it was an architectural integration. It allowed Nvidia to control and optimize the entire nervous system of the AI data center, not just the cerebral cortex.
He successfully integrated the brain and the nervous system.
Yes.
Now, let's fast forward to the current state of play in 2026.
Okay.
The Ridgeway Record Source provides a fascinating analysis of how NVIDIA is leveraging this integrated architecture to completely suffocate their competition.
Yeah, they have aggressively shifted their manufacturing cadence to what they call the one-year rhythm.
And to appreciate the severity of this shift, you have to understand the historical pacing of semiconductor manufacturing.
Right. For decades, the industry operated comfortably on a 2-year release cycle, historically aligned with Moore's law.
Because engineering a new microarchitecture, achieving a successful tape-out, securing foundry allocation, and scaling global manufacturing is a monumentally complex logistical undertaking.
It takes time.
But NVIDIA, recognizing their dominant market share and the desperate attempts of competitors to catch up, intentionally accelerated this cadence to a brutal, relentless one-year cycle.
And the roadmap outlined in the sources is exhausting just to read.
It really is.
We saw the Hopper architecture deployed in 2022, that was followed by Blackwell in 2024, then an accelerated iteration, Blackwell Ultra, in 2025, and now the Rubin architecture in 2026.
Picture an elite athlete running a marathon.
Okay.
Now imagine that athlete deciding to run the entire 26.2 miles at an absolute anaerobic lung-burning sprint.
That is NVIDIA's operational posture.
Their competitors are scrambling to procure a Hopper chip, reverse engineer its architecture, and spend 2 years desperately designing a viable alternative.
But by the time that competitor finally tapes out their Hopper equivalent chip, NVIDIA has already flooded the market with Rubin.
They are perpetually 2 full generations ahead of the pursuit.
It is a strategy of competitive exhaustion. They are weaponizing their operational velocity.
Speed is a moat.
Exactly. Speed as a moat is a profound evolution of traditional corporate defense. They are not merely relying on patent portfolios or locked software ecosystems like CUDA to protect their market share.
They are defending it by operating at a frequency that exceeds the physical and organizational capabilities of their rivals.
Which raises a massive operational question.
Yeah.
Wall Street demands reliability. Executing a hardware tape-out every 12 months with absolute zero margin for error is an operational tightrope.
How does a 30,000-person enterprise sustain that level of kinetic velocity without entirely collapsing under the weight of its own internal bureaucracy?
The answer lies in NVIDIA's highly unconventional organizational topology. It's often referred to as the flat stack.
A flat stack. Because if you analyze the organizational chart of 99% of Fortune 500 companies, they are fundamentally modeled on military hierarchies.
Right, a strict command and control structure.
Strategic information originates at the executive level, filters down to the vice presidents, then the directors, the managers, and finally reaches the individual contributors executing the work.
And in those traditional structures, corporate power is hoarded by intentionally restricting access to information.
But the sources reveal that Jensen Huang actively manages between 40 and 50 direct reports.
Which directly violates every foundational principle of standard management theory.
Absolutely.
But it lines perfectly with Conway's law.
Which states that an organization will inevitably design systems that mirror its own communication structure.
Right. And Jensen's philosophy inverts that. He believes an organization's internal structure should explicitly mirror the architecture of the primary product it builds.
Oh, that's interesting.
NVIDIA engineers a highly integrated computing stack. Silicon hardware at the base, system architecture in the middle, and parallel processing software at the top.
Therefore, the corporate hierarchy is flattened to resemble a parallel computing cluster rather than a linear military chain of command.
They operate under a specific cultural doctrine. Mission is the boss.
Mission is the boss.
It essentially dictates that an employee's directive doesn't come from a vice president's ego. It comes from the objective requirements of the project.
And Jensen illustrated this perfectly in the interview.
He did.
He described sitting in a highly technical meeting focused on autonomous robotics. The room was populated by recently graduated junior engineers, senior vice presidents, and executive staff.
Everyone in one room.
Right. And when a critical strategic pivot is heavily debated and finally resolved, the junior engineer hears the conclusion at the exact same millisecond as the executive VP.
There is no informational filtering.
There is no multi-week delay while a strategic memo is drafted and trickles down the chain of command.
And by democratizing the flow of strategic information, you empower the specific individuals who are closest to the actual engineering problems to make highly localized decisions instantaneously.
You eradicate the paralyzing friction of middle management.
Right. Now, this structure places an immense, almost crushing burden of performance on the individual because you cannot hide behind a bureaucratic title or a rigid job description.
But the resulting organizational agility is staggering.
It is.
And logically, you would assume that placing employees in a high-pressure, flat-structure, perpetual sprint environment would result in catastrophic burnout and massive turnover.
Naturally.
But the data from the FY24 sustainability report completely contradicts that assumption.
It does.
The semiconductor industry is notoriously grueling. The average employee turnover rate is 17.7%.
17.7.
NVIDIA's verified turnover rate is 2.7%.
2.7. That is a staggering metric.
Statistically, nobody voluntarily leaves the company.
And that 2.7% retention metric is a direct reflection of a highly optimized compensation and welfare infrastructure supporting their 29,600 employees.
The sustainability report details an aggressive commitment to employee well-being.
They have empirically achieved and continuously audit true base pay parity across gender, race, and ethnicity.
They deploy comprehensive, high-cost welfare benefits, including full financial reimbursement for adoption, surrogacy, and complex fertility treatments.
And perhaps the most crucial pressure release valve. They implement 8 fully paid, company-wide recharge days annually,
The entire global organization simply ceases operations and unplugs simultaneously.
which prevents the anxiety of returning to an overflowing inbox because everyone was off.
Exactly. Furthermore, their board of directors is 50% racially or gender diverse.
Demonstrating that a commitment to structural inclusion isn't just an HR initiative. It is embedded at the absolute highest level of corporate governance.
So when you synthesize a mission-driven culture operating at the absolute frontier of computational science, with a welfare infrastructure that genuinely stabilizes the employee's personal life,
A 2.7% turnover rate becomes a logical outcome, not an anomaly.
it's a holistic approach to corporate sustainability, which naturally necessitates a pivot to the broader global implications of their technology.
Right, the environmental impact of the AI industrial revolution.
We must rigorously examine the thermodynamics of this era.
Yes, training frontier AI models requires an astronomical volume of electrical power.
And as generative AI scales globally, the energy demands are generating severe, legitimate concerns regarding grid stability and carbon emissions.
The energy paradox. It is the defining friction point of the current tech cycle.
Because if you consume the surface-level critiques, the deployment of massive GPU clusters is going to boil the oceans and destabilize national power grids.
But Jensen Huang reframes this entire debate through a longitudinal lens.
How so?
His core thesis is that while training an AI model undeniably consumes massive amounts of energy, the subsequent application of that trained model exponentially saves energy across global industrial sectors.
And we can actually quantify that thesis using the metrics provided in the sustainability report.
Yes, let's analyze the hardware efficiency first.
The new Blackwell architecture GPUs are fundamentally 20 times more energy efficient than traditional CPU infrastructure for executing specific AI and high-performance computing workloads.
20 times.
If the global computing industry transitioned all of those specific, highly intensive workloads from legacy CPU servers to GPU-accelerated infrastructure,
The net reduction in power consumption would be approximately 30 trillion watt-hours of energy annually.
30 trillion watt-hours. To contextualize that figure, that is sufficient to power roughly 4 million average American households for an entire year.
And additionally, Nvidia's architecture currently powers 7 of the top 10 most hyper-efficient supercomputers on the global Green 500 list.
The hardware efficiency is impressive, but the software applications are where the energy paradox truly resolves itself.
Absolutely.
The sources highlight a specific initiative executed by Microsoft utilizing NVIDIA's accelerated computing stack.
Microsoft deployed AI to screen and simulate the chemical properties of 32 million potential battery material.
32 million.
And the AI accomplished this in roughly 1 week.
1 week. And the output was the discovery of a radically new electrolyte material that possesses the potential to reduce the required volume of lithium in battery manufacturing by 70%.
70% less lithium.
If you rely on traditional human material scientists operating in physical laboratories, testing 32 million distinct chemical permutations would take decades.
If not centuries.
Exactly. Yes, the AI cluster consumed a massive volume of electricity during that 1 week of computation. But the resulting output is a battery architecture that could fundamentally decrease global reliance on highly destructive, energy-intensive lithium mining operations permanently.
That specific application is exactly what Jensen Huang defines as digital intelligence driving physical industrial productivity.
And NVIDIA's most ambitious manifestation of this philosophy is their simulation platform known as the Omniverse, and a highly specialized project designated Earth-2.
The Omniverse concept is fascinating.
Imagine taking the underlying physics engines used to render hyper-realistic, massively multiplayer video games.
But instead of using them for entertainment, massive industrial conglomerates utilize them to construct flawless digital twins of physical reality.
Suppose a manufacturer needs to construct a billion-dollar automotive assembly plant.
Historically, you draft architectural blueprints, pour the concrete, install the robotics, and pray your theoretical efficiency models were accurate.
With the Omniverse, you construct the entire facility in the simulation first.
You simulate the exact kinematics of the robotic arms, the thermal dynamics of the HVAC system,
The precise physics of the conveyor belts, and even the natural lighting.
You run the factory at maximum capacity in the simulation for virtual years, identifying every microscopic bottleneck, every wasted kilowatt of energy, and every logistical collision long before you break ground in the physical world.
It is the ultimate macro-scale realization of their 1997 RVA 128 strategy.
Exactly. Prefetch the future.
Stress test every variable in a flawless simulation before committing a single dollar to physical reality.
And with Earth 2, they are scaling that methodology to the entire planet.
Earth 2 is literally a digital twin of the Earth's global atmospheric and weather systems.
Historically, meteorology relies on immensely computationally heavy physical equations to model fluid dynamics.
Earth 2 abandons that approach.
It utilizes deep learning models trained on decades of historical weather data to recognize and predict atmospheric patterns.
And the result is a system capable of predicting complex global weather phenomena 1,000 times faster and 3,000 times more efficiently than traditional supercomputer modeling.
3,000 times more computationally efficient.
The cascading benefits of that capability are staggering. It ranges from providing governments with highly accurate, hyper-localized predictions of extreme weather events like hurricanes,
To allowing global shipping conglomerates to dynamically optimize their supply chains to avoid climate disruptions.
However, possessing the capability to flawlessly simulate industrial infrastructure, invent novel chemical compounds, and predict the global climate, it necessitates a serious conversation regarding the safe and reliable deployment of these foundational models.
Unquestionably. Nvidia is acutely aware that by providing the primary computational engines for the AI revolution, they inherit a profound responsibility for the parameters of its deployment.
The sustainability report explicitly details their frameworks for deploying trustworthy AI.
They are not simply shipping raw compute power, they are actively engineering guardrails.
For instance, they have developed a toolkit called NEMO Guardrails.
This software layer is specifically designed to ensure that conversational AI models, the underlying architecture for enterprise chatbots and digital assistants, remain strictly factual, secure, and operate within the defined parameters of their intended use case.
They are also heavily invested in a transparency initiative known as Model Cards ++ Plague.
And to understand this, imagine the highly detailed nutritional label printed on the back of packaged food, but applied to a complex neural network.
A model card provides developers with absolute transparency regarding exactly what data sets the AI was trained on, what its inherent mathematical limitations are, and the specific parameters under which it was tested.
NVIDIA has enhanced and published over 100 of these detailed cards, ensuring that developers integrating these models into enterprise software have total visibility into the architecture they are deploying.
It is a systemic acknowledgement that raw computational capability must be firmly tethered to rigorous deployment standards.
And this transitions us to the macroeconomic and geopolitical implications of the entire AI industrial revolution.
We must examine the immediate future of the labor market and the complexities of global trade.
Let's address the persistent anxiety surrounding AI and employment.
Whenever the discussion turns to AI autonomously generating code, predicting complex weather patterns, or automating logistics, the immediate societal fear is the prospect of massive structural unemployment.
However, the source material introduces a compelling economic framework to analyze this transition, the Moritz corollary to Moore's Law.
Named after Mike Moritz, another legendary partner at Sequoia Capital.
The fundamental premise of the Moritz corollary is a counterintuitive observation regarding technological advancement.
The theory states that as fundamental computing power becomes exponentially cheaper and more universally accessible, the total addressable market for technology actually expands massively, rather than contracting.
Jensen Huang applies this exact economic logic to the deployment of artificial intelligence.
His historical perspective is that continuous productivity increases are the direct driver of broader societal prosperity.
When a corporation utilizes AI infrastructure to become vastly more productive and highly profitable, the historical precedent is not that they immediately terminate their workforce and culturally stagnate.
Instead, intrinsic human ambition takes over.
The corporation leverages that newly generated prosperity to aggressively expand its operations, to fund the research and development of entirely new product categories, and to pursue larger markets.
This expansion inherently creates entirely new categories of employment that were previously unimaginable.
Humans have infinite ambition. That is the defining quote from the analysis.
Humanity does not simply declare victory and cease operations when a task becomes highly automated. We immediately utilize the freed capital and time to attempt something significantly more complex.
AI is simply the next exponentially powerful lever to amplify that inherent ambition.
However, while human ambition may be infinite in scope, the current operational reality for Nvidia is strictly constrained by shifting geopolitical borders and volatile international trade policies.
It is imperative to analyze the highly complex geopolitical minefield NVIDIA is currently forced to navigate.
According to the detailed reporting in the Guardian source, Nvidia's unprecedented ascent to a $3 to $4 trillion market valuation in 2026 is occurring against a backdrop of severe global trade friction.
The reporting specifically highlights the intense complexities of managing a global semiconductor supply chain under aggressive tariff regimes and the ongoing, highly volatile technology trade war between the United States and China.
And we must be explicitly clear to you, our listener. We are not adopting or endorsing any specific political posture here.
We are impartially reporting the macroeconomic facts detailed in the source material.
The objective reality of the global economy in 2026 is that advanced semiconductors are the new geopolitical oil.
They are the absolute foundational strategic resource of the 21st century.
Consequently, international tariffs, stringent export controls, and sovereign trade disputes dictate exactly where these chips can be physically fabricated,
Which nation-states they can legally be exported to.
and the ultimate capital cost of the infrastructure.
Precisely. Regardless of the underlying political philosophies driving these international trade policies, NVIDIA is positioned directly at the epicenter of the disruption.
However, their unique status as the architect of the underlying ecosystem provides them with a remarkable degree of structural resilience.
They are not navigating these incredibly turbulent geopolitical waters by explicitly aligning with political factions.
They're navigating them by ensuring their underlying CUDA platform and GPU architecture remain deeply embedded and entirely indispensable to the broader global economy.
From highly advanced climate research facilities in Taiwan to massive enterprise software deployments in the United States.
Every modern digitized nation relies fundamentally on NVIDIA's architecture to remain competitive in the new industrial era.
That indispensability brings us to the conclusion of this massive analysis.
We have mapped an incredible 30-year corporate trajectory today.
We started in the desperate days of 1997, observing a company with merely 6 months of capital remaining, risking its entire existence on a single graphics architecture.
Enduring the agony of simulating software at 1 frame per hour.
We analyzed their immense psychological fortitude, absorbing 80% market devaluations to force the CUDA parallel computing platform into existence.
We tracked their realization that mathematical predictability supersedes causality, driving a relentless 15-year pivot away from the desktop PC and directly into the data center.
We saw them fundamentally alter the laws of networking physics by acquiring Mellanox to bypass the latency constraints of Ethernet.
And now, we see them operating on a punishing 1-year hardware cycle, sustained by a flat, highly compensated neural network culture, utilizing their silicon to literally simulate the Earth's atmosphere to mitigate climate disasters.
The unifying architecture beneath all of those discrete events, the unbroken thread connecting the RIVA 128 in 1997 to the Rubin architecture in 2026, is the disciplined philosophy of anticipation.
It is the absolute commitment to navigating toward the $0 billion market.
NVIDIA's dominance is not merely a function of fabricating the fastest microchips. It is entirely predicated on having the institutional courage to continuously prefetch the future.
To flawlessly simulate reality in a synthetic environment before committing capital to build it.
And to aggressively fund the development of platforms an entire decade before the broader market even possesses the vocabulary to request them.
Thank you for dedicating your time to join us on this extensive deep dive. We have unpacked a massive volume of highly complex architectural and economic theory today, but hopefully you now possess a highly detailed, foundational understanding of the underlying mechanics driving this AI revolution.
Before we conclude, I want to present a final, highly complex concept for you to consider.
Okay.
We have discussed at length NVIDIA's ambition to construct digital twins of massive manufacturing facilities and the Earth's entire climate system within the Omniverse to predict thermodynamic inefficiencies and forecast global weather. But consider the philosophical tipping point we are rapidly approaching. If generative artificial intelligence and high-fidelity physics simulators like Earth-2 become so mathematically advanced and so unimaginably accurate that their synthetic simulations are entirely devoid of error.
What happens?
What occurs when the digital twin becomes statistically more reliable than our actual physical observation of reality itself?
Hmm?
When we cease looking out the physical window to observe the weather and instead consult the simulation to dictate what the sky is mathematically required to be doing.
That is an incredibly profound, slightly terrifying, but undeniably fascinating paradigm shift to consider. Keep questioning the underlying architecture. Keep exploring the limits of the simulation, and we will see you on the next deep dive.